Hi, everyone. Welcome to the Young SECED podcast series. Today, we're bringing a special guest from ARUP. His name is Sebastian Kaminski. He's an associate structural engineer at the Specialist Technology Analytics and Research team at ARUP. And we are bringing him in this podcast because he's been doing very interesting work in seismic engineering. Not only that, other things as well, other fields, and we'll be exploring a bit more tonight. We'll first focus on Sebastian's career and how he got involved in the work that he's been doing. And then we'll focus on a specific project, a very exciting project that I'm sure you'll enjoy hearing about. So first of all, Sebastian, welcome. Thank you for joining us. And would you like to introduce yourself?
Yes, thank you very much for having me today. So my name is Seb Kaminski. I'm a structural engineer at ARUP. I've been at ARUP now around 18 years, I think, and I specialize in seismic design and design using bio-based materials such as timber and bamboo, and design in developing countries.
All right. Cool. So I've had the privilege of working with you for the last 3 years, so I have some knowledge of what you have been doing. But for the audience that don't know too much about your work, I have a few questions just to set the scene. So first of all, you've had a fascinating career that combines structural engineering, seismic design, and humanitarian work. So to begin, could you tell us what first drew you to engineering? And were there any early experiences or influences that shaped your interest in structures of the built environment in general?
So I think I was always interested in engineering and structural engineering since school, and then I studied just normal civil engineering at Imperial College. And in my second year, there was a project called the El Salvador Project, where a group of students would go out every year to work with vulnerable communities in El Salvador. And I was lucky enough to go out in 2005, and go out again in 2007 as team leader. And in 2005, that really opened my eyes to working in developing countries, to the needs in developing countries. And we built, in total, I think we built around 12 houses for low-income communities that were very vulnerable. And the houses were made of steel and a local type of bamboo. And they were designed to be earthquake resistant. So that really opened my eyes to how good structural engineering can positively affect communities, and just seeing how vulnerable the communities were to earthquakes also was very eye-opening for me.
And so my understanding, and correct me if I'm wrong or expand on the topic, is that somehow you still get involved in some projects, in advising some of these university projects. How have you seen the students' involvement in these projects over the years since you've left university, but you've kept some involvement? Are they the same? Have they changed?
So that's an interesting question, and that's where international development has, I would say, matured. So in the past, there used to be a lot more of these initiatives where people would go out, students, volunteers would go out and work in these countries. Now that's sort of frowned upon, and actually for good reason. It's seen as a bit of a colonialist white savior type tendency, and I think quite rightly. It's good to use our skills to support communities in developing countries, but one has to do that with respect and care, and one has to do it appropriately. And although my experience as a student was one of the reasons why I moved into the field, unfortunately, I think it's not something which we as a community should continue to support. It really needs to be, these sort of projects should be really done by specialist organizations working closely with the communities, but led by the communities. So if people are interested to volunteer, I would say just be very aware of exactly how are you working with these communities, is the local organization that you're working with, are they working appropriately there? What are the skills that you're bringing? What are the benefits of you traveling all the way out there to work in a vulnerable community? Are you actually bringing anything, or is it more for your own experience?
So you've mentioned your experience in El Salvador and your work experience as a university student going into these communities. How did that make you think about the type of work and the type of company you wanted to work for, and how did you end up at the Specialist Technology Analytics and Research team at ARUP?
So ARUP's always been very highly regarded. So at university, I applied to ARUP. I could see they've done a lot of really interesting projects around the world. I applied to be a general structural engineer. And after around 2 years in ARUP, I got in contact with the NGO that I'd been working at in El Salvador. And they asked if we could review the design they had developed for El Salvador for affordable housing, and if we could give a formal letter of approval, which would enable them to get more funding. Now, ARUP has an internal fund, pro bono fund, which covers ARUP's own employees' time to do charitable activities. So I applied to that, and I received some funding to do that assessment. I worked with a number of excellent structural and seismic engineers to get really good feedback on the design. And using that, we started to develop or started to explore alternative forms of housing that we thought would be more appropriate, more resilient, and more durable. And then I came across the iStruct Paid in Lee Award, which I applied for. And that enabled me to go out to Latin America, to Colombia, Costa Rica, and Ecuador, where I did research on bamboo housing. And with that, we started to develop a concept for an improved bamboo house, which was even more seismically resistant.
Okay. Right. And over since you've started working at ARUP, I'm aware that you've worked with an impressive range of materials. So, for example, reinforced concrete, steel, masonry, but also timber and bamboo, as you've just mentioned now. What has led you to work with such a variety of materials, and does that tell something about the range of work that the Specialist Technology Analytics and Research team at ARUP does? Yeah, if you can say, for example, how you've been involved with, if we focus in seismic engineering, what type of projects do you usually get involved with?
So as a building engineer, I mainly did concrete and steel, reinforced concrete and steel. And then when I went to STAR, I started to work more in projects in developing countries. And I worked more on timber and masonry. And in developing countries, one has to use what technology is most appropriate for the context. And it's rarely steel, but it's often reinforced concrete, timber, bamboo, or masonry. So I started to get more experience in the other materials and how to use them appropriately in those contexts and how to make them seismically resistant.
And because of the breadth of regions and countries that you've worked in, that's where you've seen all these breadth of materials, and you've had to work with all these materials. So depending on the context, you tend to see different materials that are specific in that country.
Exactly. Unreinforced masonry and reinforced masonry are very common in developing countries, whereas sometimes you don't see often reinforced masonry, for example, in Europe.
Okay. Right. So you've also worked in post-earthquake contexts, as I'm aware, such as Haiti, Nepal, and Ecuador. Could you tell us a bit more about the specific work that you conducted in those post-earthquake contexts, and what have those experiences taught you about the relationship between engineering and human resilience?
So in Haiti, I ran a training course for local students on the structural use of bamboo. And that was quite a few months after, actually, sorry, that was quite a few years after the earthquake, sorry. So the damage had generally been cleaned up. In Nepal, we ran a local training course on the use of timber and bamboo, and that was several months after the event. So we were already in the recovery phase. Ecuador was only about 2 months after the event. I went along with EFIT, which is the UK Earthquake Engineering Field Investigation Team, to conduct a review of building damage immediately post-earthquake, and it was generally still quite fresh then. So we could see a lot of the buildings that had collapsed and buildings that were damaged. And so we reviewed that to get very useful data on building stock.
Has that changed or made your engineering practice any different after you visited those countries? And if so, how so?
I think learning about or seeing building damage, one learns a lot from that. So on those particular trips, I have worked a lot closely with local communities. On those particular trips, I wasn't able to experience or learn from how communities responded. But I saw how buildings responded. So yes, one learns a huge amount of that, seeing earthquake damage in real life, seeing the different damage patterns which you learn at university and which you try and design for. It's very, very useful. And you can see sometimes why buildings have suffered. You can see, well, that design doesn't look quite good, or that element's quite congested. You can start to at least estimate why building damage has occurred and learn from that.
Right. So you've already mentioned the Pilene Award, which, as you said, is an award run by or sponsored by the Institute of Structural Engineers in the UK. And could you tell us a bit more about the award? How did your idea come about? I think you have mentioned that El Salvador trips shaped that. So how did you frame your application? What do you think made you get it? And then if you could just run us a bit through the journey that you went on during the award.
So that was recommended from a colleague at work, and I would encourage everyone who's listening to also apply to that. It's an excellent award. It gives people a very good opportunity to do a lot of research in another country. And I was lucky enough to get it. And I basically phrased this as something novel because that data hadn't been existed. That data didn't exist. I was focusing on modern bamboo houses in developing countries. And I selected a variety of countries, 3 specific countries, Colombia, Ecuador, and Costa Rica, to focus on. And I had already started to make contacts in all 3 of those countries, and that was very handy. So I used those countries to basically flesh out my application form, so I had a very clear idea of what to do.
And what made you want to focus on the modern bamboo housing? What made you curious in regards to that type of housing and not other types of housing?
So when the NGO from El Salvador asked us to review the housing they had done, it was a slightly unusual form of housing in that it was an improved wattle and daub type house. So we conducted research on how does that behave, and that's when we came across the other examples of improved wattle and daub in Ecuador, Costa Rica, and Colombia. And there were some papers on those, but we thought it'd be very useful to actually see them in person. And so I used that award to basically do in-person inspections of housing there and interviews with the occupants and find out people's perceptions.
So I'm aware that the wattle and daub system, as you've mentioned, is sort of present throughout the world in different ways. Could you specify a bit more on what the Latin American version of the wattle and daub is, and what then was improved to make the modern version of this system?
So all countries around the world have a form of wattle and daub. It's a very clever system. It uses a bio-based material, either timber or bamboo, for the frame and the matrix, and then mud, clay, or manure for the walls. And the roof is typically clay tiles or maybe palm leaves in hot tropical countries. The foundations might be unreinforced stone masonry. In the UK, that naturally developed into timber housing, Victorian housing with lath and plaster. Sort of the natural evolution. Obviously, the plaster there is no longer mud. It's much better than that. In Latin America, the traditional wattle and daub evolved into what's called bajareke, and there's different formalities of that. And the more formal system has, in the past few hundred years, has been used for high-end housing as well. So the more well-off communities would also live in that form of housing. And the walls still were made of timber or bamboo, and mud, but very cleanly finished, and the housing looked very comfortable. so it was regarded as high-end housing. And their frames were properly cut. This wasn't just informal wattle and daub from just cut tree logs. This was sawn timber, sometimes bamboo, but with very, very good carpentry connections.
And then you got involved with a specific project in El Salvador, right? Could you tell us a bit more on how that happened? How did you go about getting involved with the modern version of the vernacular that you've just explained? And then I'm also aware that it won an ISTRUCT Sustainability Award. So if you could walk us through a bit of that, how that came about.
So that started off with the NGO approaching us, as I mentioned before, and that led to some research that we did. That led to the Palin Lee Award. And then from all the work we did, we put together, and we thought, well, actually, the work in especially Costa Rica and Colombia at that time is really good. And those houses, they work, they function, they're durable. I inspected them after 20, 30 years of use, and they're in excellent condition, and people really like them. So I felt this had a lot of potential. Now, we want to develop something for El Salvador. We wanted to use a very similar system, but using more local materials for El Salvador. So naturally, it'd be slightly different. And the data wasn't there for that. So I applied for an IC Research and Development grant to do testing at Imperial College London. We did full-scale in-plane shear tests. I had to ship over the bamboo from El Salvador for that, which was an adventure in itself. And so we did really good tests. And then we also did some tests in Cambridge on a small shake table they built. We tested the wall outer plane. We also tested some of the bamboo in Coventry, bending. And we did a full-scale test in Guatemala. The combination of all of that testing gave us a lot of confidence that this system could resist very large earthquakes. And then once we had the final design, we built 3 prototypes in El Salvador. I visited them just last year with you, Rafik, and they're still in excellent condition, and the community was really appreciative of the work, and they were very happy with the designs. And we applied for an ISTRUCT award, and we were lucky enough to get that, and that was the Sustainability Award we won. I think it was back in 2016.
Yeah, that's great. I was indeed there last year, and it was amazing seeing the houses still in very good shape, and to hear the people's opinions on the houses. They're very positive opinions. And so then, in your opinion, what makes these a sustainable design? Why can we call this a sustainable design?
So the word sustainability gets thrown around a lot, and we have to be very careful with it. People call lots of things sustainable when they're not really sustainable. So what is sustainable? I think sustainable, I'm not going to give the best definition, but in my view, one has to look at something holistically. So is it truly low embodied carbon over the entire life cycle of the building? When I say truly, I mean, is it in an unbiased way? Have we done the analysis properly? Have we taken into account transport? And have we taken into account end of life? And have we taken into account how long the building will last? Because if you have a bio-based material that only lasts 5 years, but has to be rebuilt every 5 years, that's not sustainable compared with a reinforced concrete building that might last 60 years, even if the reinforced concrete building has a much higher embodied carbon to begin with. So we have to look at the building across its entire life cycle. And we design the buildings to have a design life of 50 to 60 years, which is the standard for buildings following most international codes, 50, 60 years with minimum to low structural maintenance. Right. Unfortunately, lots of bio-based buildings out there at the moment, especially in bamboo, don't last that long because they have all the timber and bamboo exposed to the elements. They look great on Instagram on day one. You visit them after 5 or 10 years, and there's serious damage. And I think, Rafik, you and I saw that, unfortunately, in some of the countries we visited in Latin America. And that was housing which inadvertently didn't really consider durability properly. So that's one part of sustainability, the embodied carbon across the entire design life, taking into account durability. The other part is, I'd say, material sourcing. Are we sourcing the material appropriately? Are we harvesting appropriately? If you're using a tropical hardwood, how are you harvesting? If it's not FSC or PEFC or equivalent, where you're getting it from, it's a good chance that it may be harvested in an unsustainable manner, which is not good. Bamboo, the one advantage of bamboo is that because it grows so fast, and because typically people only harvest bamboo when it's mature, that means that you rarely actually damage the plant. So bamboo is different from timber. Timber, when you cut timber, that plant dies because each tree is its own plant. Bamboo is actually a plant underground. So if you harvest one cane, the plant stays intact. The plant can keep growing individual shoots of bamboo. And so provided you harvest it normally, when each individual calm is mature, the plant doesn't die, soil cover remains, and it'll keep producing shoots for around 100 years. So bamboo is naturally more sustainable, but you still have to harvest it properly. But we made sure we harvested it from appropriate sustainable sources, and the timber was FSC certified as well. So I think you have to look at sustainability more holistically to be truly sustainable.
Right. Okay. And we've mentioned bamboo a few times now. A few listeners might already know some of the properties that make it an appealing structural material. In your opinion, what makes bamboo an attractive and appealing structural material for some solutions such as this one?
So obviously sustainability is a really important point, as I mentioned, and its speed of growth as well. You can harvest each calm within 3 to 5 years, compared with timber, which is typically 40 to 60 years at least. Bamboo as a material, it's a good strength to weight ratio. It's similar to, I would say, a hardwood in terms of strength, which is very good. It has downsides. Unfortunately, it's not very durable at all. It's similar to a not very durable timber. It's also hollow, which makes connections quite difficult. And it also has a tendency to split probably a little bit higher than timber. So it's a bit trickier to design with, but at the same time, it has a lot of advantages. And sometimes you can build with structural bamboo up to 100, 150 mil in diameter. And that's really big. And that's basically a structural element that's ready to use. And you don't need to cut that down. You can use that directly for beams and columns. So it does have a lot of advantages.
So now focusing on this enhanced, let's say, vernacular structural system. So the what we've termed, or what if the community has termed as the composite bamboo shear wall systems. Other people use other names, but essentially it's the same system. Could you set the scene on how this structural system has been used throughout the world, and what traction it's been getting? Where can we see these houses? And, yeah.
The history of composite bamboo shear walls dates back probably mainly to Colombia over 100 years ago, where there were several earthquakes and people noticed that the traditional bamboo and wattle and daub system, known as bahadeki, performed quite well. And so they built more of that. And over time, as cement was introduced, they started to replace the mortar, the mud mortar, with a cement-based mortar. And that made the system more durable. In the 1990s and late 1980s, there was a big project in Costa Rica where they took those learnings and they built several thousand houses as part of a UN-sponsored program on 1 to 2 story houses for vulnerable communities, and that was very successful. Unfortunately, that project didn't continue, but mainly for political reasons. And then in 1999, after the coffee growing region earthquake in Colombia, it was noted that a lot of the traditional bamboo houses performed quite well. That spurred a lot of research in Colombia, and there they wrote the world's first country-specific bamboo code. And they also developed some bamboo guides. And after the earthquake, they built several thousand bamboo homes as well. Those are all composite bamboo shear wall systems, and those are the ones that we saw when we visited. And so after that, there was a lot more material that's produced, lots of guides, the code started to be developed more, and that was all really good for the bamboo industry. There wasn't much traction after that, after about 2000, 2004, unfortunately. This interest in novel materials sometimes appears after an earthquake, but only temporarily, and then dies down. But Base Baha'i over the past over 10 years have been working in the Philippines and Nepal in India, and they have built several thousand composite bamboo shear wall houses very successfully. They've actually taken that technology from Colombia and they've adapted it for the Philippines and also made it typhoon resistant, and that's very exciting. So now in total, we estimate there's over 10,000 composite bamboo shear wall homes, modern ones, that have been built since around 1990 worldwide, mainly in Costa Rica, Colombia, Nepal, and the Philippines, but more and more worldwide. There's some in El Salvador, there's some in Mexico, Ecuador, Peru, and India.
That's amazing. That's really good to hear. And so we've already mentioned that these houses can be made to be resistant to earthquakes, and now you've just mentioned typhoons. Could we dig a bit deeper into how exactly these houses can be designed to be earthquake and typhoon resilient, and what about them? What details make these houses quite good in resisting these forces of nature?
So there's a bit of a misconception that timber and bamboo behave automatically well in earthquakes because they are flexible. That's actually sort of false. The main reason why traditional timber and bamboo buildings behave well in earthquakes, there's several reasons. Firstly, because these materials have a good strength to weight ratio, the buildings tend to be light, and the force that you need to resist in an earthquake is proportional to the mass. So a lower mass means lower force. Reason number one. Reason number two, traditional timber and bamboo buildings tend to be quite well tied together, so they can distribute the forces quite well, unlike traditional masonry buildings, which don't have the same degree of tying. Reason number three, traditional timber and bamboo buildings have the ability to absorb small amounts of energy through damage and dissipation in connections, especially. And reason number four, when timber and bamboo buildings tend to collapse because they are lighter, they're less likely to lead to fatalities. So those are the four main reasons why traditional timber and bamboo buildings behave well in earthquakes. Now, in our case, we have something which is modern, but it's still based on that vernacular, but improved. But it has similar principles. So firstly, in terms of the mass, we have a system which is quite light. So the system is basically a modern composite bamboo shear wall system. It's a timber or bamboo frame that's treated against insects with a matrix of timber or bamboo, or in some cases, a light metal mesh. And again, the timber or bamboo would be treated. And we finish the walls with a thin cement render. We've chosen cement because it's more durable. We're aware it has quite a lot of embodied carbon in it, but still comparing that to the embodied carbon of a reinforced masonry house with a similar seismic performance, we have about half the embodied carbon. And several independent studies have shown that. But back to the seismic performance. So our system, firstly, as I mentioned, is quite light and also has the ability to dissipate energy through basically damage in the connections and small amounts of cracking in the walls, which is controlled. So the in-plane shear wall tests that have been done around the world have demonstrated that this system can have quite a lot of ductility.
And if we now focus a bit more on durability, which is an essential part of something being sustainable, because we want something to last for as long as we can make it last given the expectations of society. When we speak about durability of these houses, what makes these houses what makes these designs durable by definition, and how we as engineers can ensure that that's the case?
So there's three main attack mechanisms to timber and bamboo that's outside of the sea. You've got beetles, termites, and rot. You can protect against beetles and termites by treatment, and we do this by treating the bamboo with boron, which is a safe-to-use salt that's widely available. Any timber that we use is either treated with boron or copper, which is also an alternative relatively safe chemical. In terms of rot, any treatments that are available that are permitted for normal residential use won't provide long-term rot treatment. It simply doesn't exist for timber and bamboo, unfortunately. So you have to keep the timber and bamboo dry, fully dry, and that means protected from driving rain and sun as well. So you've got to keep it completely within the waterproof envelope and completely within the rain shadow. And you can identify that if you take your roof overhang, and you draw a 45-degree line. Where that roof overhang line hits the building wall, everything below that, you should consider that to be vulnerable and exposed to driving rain and sun, and will have a limited design life. Everything above that is likely to last 50 plus years because you're inside that rain and sun shadow. And that's been determined, that's already in several codes, and that's been determined independently through various studies. It's really, really important not to have your timber and bamboo exposed to the rain and sun. And that's exactly what we did. We have a good roof overhang. We've elevated the structure above ground. We've got a damp-proof membrane to separate the masonry upstand from the timber and bamboo frame. And then we have a cement mortar, which acts as a waterproof coating to protect the timber and bamboo frame. And we've left the timber fully exposed on the inside so that it can breathe. So any moisture that does get absorbed by the wall in the more in the rarer, larger rainstorms, at least the walls can dry out from the inside. And we reviewed housing in Costa Rica, which has been there for 35 years and is still in excellent condition when those design requirements for durability have been incorporated. So we're confident that can work, but the timber and bamboo has to be fully protected against rain and sun.
Okay. That's really encouraging. So when you've seen these principles being followed, the houses actually do quite well with time, and they've resisted earthquakes. Is that right? Some earthquakes have actually occurred, and these houses have resisted them, and people still live in these houses. Is that right?
Yes. No, I think no large events. There was one in Limon in Costa Rica. I forget when, a few decades ago, and that was after some of the houses were built, and apparently the houses performed very well, but they were still quite young. But in terms of the other composite bamboo shearwall houses around the world, as far as I'm aware, they haven't yet experienced a large event. But I think we can be pretty confident that, provided from a durability perspective, they had those criteria incorporated, then they should perform pretty well even after several decades of use.
Amazing. And in your experience so far as a structural and seismic engineer who has worked in so many different contexts, is this one of those designs that really performs well? Have you seen other designs in other places? How would this design compare to other designs for similar contexts?
For housing in general, for using bamboo or bio-based materials?
I'd say for housing. So these houses does quite well in rural and semi-rural places, where there's timber or bamboo. Have you seen any other structural solutions that are sustainable, durable, earthquake and typhoon resilient, and that use local materials? Is there any other competing design that you've seen in other places that you think that quite well?
I would say there's not many that satisfy all of those criteria, unfortunately. So one of the most durable and easy to build systems is reinforced masonry or confined masonry. That's very common around the world, and that is a very, very good system. Unfortunately, it does have an high embodied carbon. If using bio-based materials, then I think this is probably the best system that we have seen that satisfies all of those criteria. I'm very open to other systems, and I've reviewed a lot of different systems around the world, but I've yet to see a bio-based system that is more appropriate for developing countries. I think one exception might be more conventional timber framed housing with, let's say, a tropical hardwood facade. So I've seen some designs like that around the world for developing countries, and that can be quite good, but you need to have a durable facade. I've also seen some interesting designs which are earthquake resistant out of stabilized compressed earth blocks around the world. I think that's an interesting technology we should explore. There are a few designs out there, but in terms of bio-based materials, in terms of bamboo specifically, I think this is the best design I've seen out there.
And we haven't actually spoken about affordability. So how affordable are these houses compared to other systems?
So this house is probably has a similar cost to a conventional code compliant reinforced masonry house, one of these countries. So this isn't a very, very cheap house. This is an affordable house. This is sort of the basic you can get. Now, many people have tried to see, can we develop even more affordable housing, even cheaper housing that's still code compliant? And I don't think you can. I think there's a line below which something has to give. And of course, if we're talking about vulnerable communities, then maybe we accept that if we're providing housing, maybe it won't have the same longevity. But at the same time, I think vulnerable communities have the right to the same resilience that we have. Our building in London doesn't fall down in a design event. California, their housing is designed so it doesn't fall down in the design earthquake. So why should a house in El Salvador be designed for a shorter design life and be designed so it doesn't have the same performance in the same earthquake? That feels inappropriate.
Yeah. So that's a nice segue to my follow-up question. So how do you see the field of seismic engineering in developing contexts? And this is from a Western perspective. So where an engineer, say in London, helps design something for earthquake loads in developing contexts. Is that changing? Has that changed? You've already mentioned a little bit, but how do you see that changing in the coming years, and how can we best help or getting involved in these projects?
I would say the level of engineering in developing countries has improved significantly over the past few decades, and that's excellent. More and more countries now have their own codes. Most countries have their own codes, and those codes are more and more up to date. And they're catching up with the state of the art, which is excellent. And the level of experience of engineers is also very good. And there's a lot of very good technologies and knowledge being developed. Confined masonry, for example, some of the best codes out there now. They're not published in Europe, they're published in India, for example, or in Peru. Some of the best work in bamboo is coming out of Colombia and the Philippines. So actually, we should definitely look to these countries for experience and knowledge. So often it's not about us teaching. That's a very colonial mindset by default. We should also learn from all other countries, I think. If we want to offer our skills, I think it's about offering them respectively and where there are knowledge gaps and being aware that we also have our knowledge gaps and we need to learn.
Yeah, it's great. Yeah. So from your experience that you've had so far, which is quite broad in terms of regions of the world, you have focused on seismic engineering in developing contexts for part of your career. Are there any important principles for designing structures in seismic regions that hold no matter where you are? So say that, given your breadth, what have been the underlying principles that have held no matter where you look at, if you're to give some pointers?
Specifically for seismic engineering?
For seismic engineering, yeah, in these contexts.
If
there are any.
Or
this
in
might be
any
a difficult
context.
question. In these contexts.
Good question. No one's ever asked me that before. I think good seismic engineering, firstly, have a robust analysis. And if you're talking about simple housing and schools, probably don't need to do advanced analysis. You're probably talking about simple analysis. You're probably talking about an equivalent static. If you're doing anything more than equivalent static, ask yourself why. Do you need to? I've seen so many mistakes when people jump to advanced analysis unnecessarily. So when I'm doing simple housing, it's nearly always equivalent static. And it means that with a small amount of budget, I've got more time to spend on important things like detailing. So detailing is very, very important. Don't always go for default details. What's actually buildable, taking into account the local context. How is what we design actually going to be built? Make sure the information that we provide is very clear, providing the information on normal drawings that we might produce for a London-based engineer, a London-based consultancy isn't necessarily appropriate for maybe working with an NGO in, say, India, which is building, let's say, a school, and the workforce there are illiterate and speak a different language. They're not going to understand what we produce if we were going to just emulate what we produce for London. So one really has to approach it in quite a different way. And you have to think about the context, what is appropriate for local context. So in many cases, that will mean the design will change naturally. The design might be easier to build, more foolproof to build, so harder to go wrong. We might have to consider local materials. They're not going to have necessarily off-the-shelf materials. What is actually available locally? What are the local skills? And how do we communicate that in a clear fashion? And instead of conventional drawings, that might be annotated, clear, colorful drawings that maybe we don't put everything on one A1 sheet because they might not have an A1 printer. So we might produce everything on A4 or A3 sheets. Small details like that are actually very, very important to make sure that we've really clearly conveyed it.
So really, it's an exercise of empathy and putting yourself in the shoes of a person who's in a completely different context and completely different country and city and office than you are, and understanding what their needs are and how they might work and how they might build. Yeah, it's an exercise of empathy to a certain extent.
I think so. And there's also an aspect of CDM in that. So UK CDM regulations do say that we have to consider the context. Right. And what we design has to be buildable. So we can't just use a UK context for a project in a developing country.
All right, so we're entering the closing chapter of our podcast. I'll ask you a broader question now, and I'm interested to know how you're experiencing these changes in our field or in our society as a whole. Really, it's a general question, so answer it however you see fit. With the advent of artificial intelligence, and this might be a question that everyone's asking each other these days, but I want to hear your answer. Are you seeing any changes in how you're conducting your work, or do you see any potential changes in how you conduct your work in the coming months or years? What's your vision for what it might look like?
For artificial intelligence?
Yeah, in engineering and in our in seismic engineering, maybe more specifically, seismic and structural engineering, if any.
I think it has a lot of potential use.
Mm-hmm.
If we use it properly. I think my concern is the same as everyone else's concerns out there, is if it's overused, if it's used incorrectly, and if it leads to de-skilling. My biggest concern is it leads to the slow de-skilling of us because we aren't going through basic checks, for example, engineering checks that we might normally, which means we're more likely to make mistakes. So I think we should use it, but we should be careful with how we use it and not try and overuse it, and be aware that some of the tasks that engineering tasks we might consider maybe a bit repetitive or maybe a bit boring, but they might be important to us because they keep our skills.
Do you see a day, and this is perhaps quite too philosophical for these podcasts, but do you see a day where artificial intelligence will actually ensure safety concerns the same way that, say, a good engineer ensures nowadays? Or to you, it just feels too far and a bit impossible that it will actually be good enough to check structures the same way we do, or that we should be doing?
Maybe at some point in the future, but I think that's so far away.
Yeah, it's not here yet. Okay. And last question: any advice that you've first of all, I'll just say it out loud, and I'm sure that the listeners will agree. You've had an inspiring career that many junior engineers can only dream of. So my last question to you is, have you got any advice that you can give to early career structural engineers? So either people starting out their careers now or just finishing their degrees, people that might have similar interests to yours and want to have similar impact to yours. Um, any general advice, any specific advice for them?
Yeah, a lot of people have asked me this. So I'd say, one, go for iStruct chartership. I'd say one learns a lot from that. Two,
Yeah.
focus on the technical. Things like project management, they can come later, but technical is really important. So the first few years, try and get very good grounding in reinforced concrete and steel. As many different materials as possible, especially now also in timber. If you can in masonry, it can be sometimes hard to get, but also working from first principles. Try and avoid overusing, let's say, complex analysis unless it's necessary. Learn those basic skills. Hand calcs, super important. And I think that's a really important ground from which one can develop and learn other skills from.
Right, that's great. I'm sure the listeners will appreciate that. Any things that I might have left out that you'd like to mention, either in your about your career or about the composite bamboo shear wall houses? Anything else that you might want to add?
No, I don't think so, but thank you. Thanks for
All
having me.
right. Yeah, it's been a pleasure. Thank you, Sebastian. I hope you've enjoyed listening to our podcast, and we'll see you in the next show. Thank you.